Welcome to the next lecture on probability and random variables. In this lecture, we will study about the distribution and density functions. So coming to a random variable, the name itself, what is a random variable? So a variable which is actually taking different values that is actually assigned to every outcome. So I have taken a symbol zeta here. X of zeta assigned to every outcome eta of an experiment. So what does it mean? So when I perform an experiment, so this is an experiment. So in that experiment, if suppose there are different outcomes, so S1, S2 and S3, these three are different outcomes. And these outcomes, if they are mapped to a real line, the numbers on the real line, then we say that the capital X is actually a random variable. The convention of random variable is always a capital letter. So the outcomes of an experiment mapped to a real number is actually termed as a random variable. So all the outcomes are actually mapped and we write that as a function. So x of s1, x of s2, so x of s3. So x is a random variable taking the values s1, s2, s3. So we can write it as a summation of for discrete, and we can write it as integration of for a continuous random variable. So coming to the distribution function. So what is actually a distribution function? So why are we coining this term is, so whenever I have to calculate the cumulative distribution function, so that means what are the values, what is actually the value of probability till a particular value. That means we take the previous values when I want to calculate a particular value. So sum of probabilities of the previous values, cumulative addition, will actually give you the distribution. So for example, there are 6 sample points in the sample space S. So let me take Fi is equal to Si, where I is equal to 1, 2 and so on, 6. So S1, S2, S3 and so on, S6. So let me take the function, the random variable x as x of Si is equal to I. So if I take S as sample space, in that I have a random variable x of s which is less than a1. So it is actually a constant here. Again, if I take the second value, which random variable is lying between b1 and b2. So similarly, you can go on assuming the values x of s is equal to c. So if I want to calculate, see, the distribution function always, it's not a particular value, but it is till a range. So till a range, how do we indicate it? So we indicate it with a capital letter F, fx of x is equal to, or you can even use simply f, capital F of x. So capital F is always showing you distribution function. So f of x is equal to probability of, in the sample space, the random variable x taking the values less than or equal to x. So what does it mean if I write less than or equal to 3? That means I have to take x of s1, x of s2, x of s3. So till that particular value I have to summate and to calculate the distribution function. So in the mind you have to get an idea that the distribution function is, when I go for a cumulative addition, definitely my distribution function will be a staircase approximation function. It is an increasing function, monotonically increasing function. So coming to a small example again. So let us take whatever we have just taken S1 to S4 as 4 sample points, with each sample point representing an event with probability. See, for example, discrete probabilities are taken. P of S1 as 1 by 4, 1 by 8, 1 by 8 and also 1 by 2. So if I have 4 different probabilities and I have to calculate x of Si, so this is a function now. If capital x of Si is equal to I minus 1.5. So I have to substitute the values of 1, 2, 3 and 4, so on. So if I substitute that, what is my first value? So if I take minus 0.5, okay, and similarly 0, yeah, 0.5, because you can take minus 0.5 and when you substitute 1 and when I substitute 2, so all the values you can take the values for x. And coming to the probabilities, P of S1, say P of S1 is equal to 1 by 4. So P of S1 is equal to 1 by 4, it means that it is less than or equal to S1. So less than or equal to S1 is nothing but 1 minus 1.5, which is minus 0.5. So at minus 0.5 I have a value of 1 by 4. Okay, so similarly I can take any other value as when I take a value, when do we get 0.5? So if I substitute 2, it is 2 minus 1.5, which is 0.5. So at that particular value, when it is equal to 2, what is the value? It is 1 by 8. So 1 by 8 plus again 1 by 4, which actually gives you 3 by 8. So these points are to be marked at a particular instant, and then it is a staircase function. So slowly it increases, and if I calculate the final value, that is at I is equal to 4 minus 1.5, which is equal to 2.5, then at 2.5 what is its value? It is equal to 1 by 2. So but it is less than or equal to 2.5, so you have to add 1 by 2 plus 1 by 8 plus 1 by 8 plus 1 by 4, which actually gives you 1. So what does it mean? The maximum value of probability will be always equal to 1. So less than or equal to 1 will get you the complete staircase approximation function. So always this is actually a small range, a bound, that the maximum value of probability according to the axioms, it is 1. And coming to its probabilities, the most important thing is based on the different values of the samples taken by a random variable, we'll approximate the distribution function. So, and for distribution function, what are its properties? So capital Fx of x or capital F of x can be used for denoting the distribution function. And coming to its properties, so for convenience, let me take f of x plus as limit f of x plus some epsilon, so it is increasing function. Similarly, f of x minus is f of x minus some constant epsilon, and this is in between 0. So coming to the first property of distribution function states that the distribution function of plus infinity, that means the right side. So when it extends to right side, we have just seen an example of staircase approximation function where the maximum value is always 1. So towards the right it ends at 1. But coming to negative, that is till minus infinity, I already told you according to the first axiom, it is non-negative. Probability is always non-negative, and if I calculate the distribution function towards negative function, it will be always equal to 0. So this is important property. And coming to the second property, it is non-decreasing function of x. So if x1 is less than x2, so then what happens? It is capital F of x1 is less than or equal to capital F of x2. So because x1 random variable is less than x2, so definitely its distribution also will be less than or equal to x2 because it is increasing function. And coming to the next property, if f of x naught is equal to 0, so some value, if it is equal to 0, then for every x less than or equal to x naught, because the probability of x naught, that is the distribution function of x naught probability, is equal to 0. So definitely the lesser values of it, so if I take x minus 1, x minus 2, that will be also equal to 0. So for all values till that x naught, till this value x naught is equal to 0. Coming to the fourth property, probability of capital X greater than small x. So what does it mean? The random variable taking greater than x. So we have just seen x less than or equal to x naught is actually a convention of distribution function. So if I want to calculate greater than x, what does it mean? It is 1 minus capital F of x. So it is subtraction. So when you do the subtraction, then we get, so see how do we write probability of x, capital X greater than or equal to x? It is actually 1 minus p of x less than or equal to x. So when I take p of x less than or equal to x, it gives you the distribution function of x. So capital F of x. This is one more important property where we use it for solving our mathematical conventions in probability. And coming to the fifth property, the function f of x is continuous from the right. So we already know that towards the right it is increasing and it is always positive, giving to 1 from the first property. The same way f of x plus is always equal to f of x, and it is continuous towards the right. And coming to another next property, p of x, if it is lying in between a range x1 to x2, then it is nothing but, you can simply write it as p of x less than or equal to x2 minus p of x less than or equal to x1. So what is p of x less than or equal to x2? It is f of x2 minus p of x less than or equal to x1, which is f of x1. So it is actually a generalized property. And coming to, this is x equal to a particular value of x, then it is f of x minus the lesser values of it, x minus epsilon. And similarly x1 less than or equal to x2. So if you see that, it is also, it can be also written as f of x1 minus the same property of 6, x2 minus x1 minus, that is minus epsilon. Okay, so x less than or equal to x2 can be written as x less than or equal to x1 union of x1 to x2. So this is actually a combination of both, and you can write it as p of x less than or equal to x1 plus p of x1 to x2. So when you have to, when the probability you want to calculate for a value which is lying in a range, then it is nothing but union of both the events. So this is how we apply the properties in solving the probability functions. So what are we actually signifying using the properties of distribution function is, fx of x is always monotonically a non-decreasing function, and it is always continuous towards the right at each point x1 and has a step of size pa at point a. So this is very, very important to note. The probability of that, the probability of value at that instant is pa. So we have already seen where is the step value in the first figure. We have seen the values. 1 by 4 is actually p of s1 equal to 1 by 4, and 3 by 8 at 0.5, and at 1.5 it is equal to 1 by 2. Okay, so this is actually the importance of distribution function. So then next is density function. So coming to the density function is actually representing the area under that particular curve. So density is always, this is an important convention, density is derivative of distribution function. So from that you can even calculate distribution is equal to integration of fx. So density function can be used for solving your problems. So let's stop here and we'll continue in the